Hello friends, in the previous video on the MCQs of module 3, that is spatial functions, we have seen 20 questions, multiple choice questions on Legendre polynomial, Bessel polynomial and few questions on Hermite polynomials. In continuation with that, in this second video we will go for remaining 20 questions on Hermite polynomial, Legendre polynomial and another very important part of this module, that is the spherical harmonics. Along with that, few questions you will find on the associated Legendre differential equation 2. So let's come directly to the questions. Now question number 1 or 21 here in the series. Hermite polynomials dash dash satisfy the orthogonality condition. 4 options are given. Option 1 do satisfy, option B do not satisfy, option C sometimes they do satisfy, and D option that is rarely satisfy. Out of this, C and D are not correct at all. Option B is correct, do not satisfy. So let's see how this particular thing is there. Now in this case, as we have already seen, the condition for Hermite polynomials, orthogonality condition for Hermite polynomial is given as my integral minus infinity to plus infinity. There is a factor, this is e raised to minus x square, and this is the additional factor we needed here to write this as hm of x multiplied by hn of x and integral multiplied by dx, and this will be equal to 0. There are two values possible. 0 if m and n are not equal. So order of the polynomial m and n are not equal, then this right hand side or this integral is found to be 0, and when this m is equal to n, this factor comes to be 2 raised to n factorial into root pi. So provided m is equal to n. So this is the condition for Hermite's polynomial orthogonality condition. So if we don't use this factor here, then this hm of x integral minus infinity to plus infinity hm of x multiplied by hn of x into dx is equal to 0. Neither give this 0 or neither give this, and that's why this orthogonality condition is not satisfied unless we multiply this integral by this factor e raised to minus x square. So in normal conditions, Hermite polynomials do not satisfy the orthogonality condition. They satisfy the orthogonality condition only when this additional factor e raised to minus x square is taken multiplication in this particular integral, and therefore question number 21, B is the correct answer, that is they do not satisfy the orthogonality condition. Now similar condition here, question number 22, for Legendre's polynomial the orthogonality condition gives integral from minus 1 to plus 1 Pn of x multiplied by Pm of x into dx is equal to delta mn, where this delta mn is Kronecker delta function, and we have to take this Kronecker delta function, we have to go for its value. So whether it is when this condition is satisfied, when we get m is equal to n, that's first option. Second option is when m is not equal to n. Third option is when m is greater than or equal to n. And fourth option is m is less than or equal to n. And therefore here the condition is very easy. This integral is found to be 0. Okay, so this delta mn or this integral value is found to be 0 if m is equal to n. M is not equal to n, and this delta mn is Kronecker delta function, and it is found to be 2 upon 2n plus 1 provided this m is equal to n. So out of this Kronecker delta function will be obtained when m is equal to n, or the order of polynomial n and order of the polynomial m, these are equal. Therefore option A is the correct option for Legendre's polynomial orthogonality condition. Provided when this m and n are equal, we get Kronecker delta function, and finally this Kronecker delta function gets value when this integral is solved. We get integral, so delta mn is equal to 2 upon 2n plus 1 if this m and n are equal. For other values m is not equal to n, this integral gives you value to be equal to 0, and for m greater than equal to n or m less than or equal to n, this integral does not give the Kronecker delta values, and therefore question number 22 correct answer is this A. When m is equal to n, we get right hand side of this equation is Kronecker delta function in the orthogonality condition of Legendre's polynomial. Now question number 23 again related to Legendre polynomial. For Legendre's polynomial, this integral minus 1 to plus 1, this is Pn of x bracket square into dx. This is the right hand side of this equation. If this integral is solved, it comes to be 2 upon 2n plus 1. So this right hand side of this integral is twice of 2 upon 2n plus 1, and hence option A is correct. So here n and m are equal, and therefore this integral minus 1 to plus 1 Pn of x multiplied by Pn of x, m is replaced by n, into dx, that comes to be integral minus 1 to plus 1. This is now Pn of x bracket square into dx, and if this integral is solved and if it is found, the correct value of this right hand side comes to be 2 upon 2n plus 1. So this is again a memory based question. You have to remember that right hand side of this integral minus 1 to plus n, Pn of x bracket square into dx is equal to 2 upon 2n plus 1. So out of these 4 options, option A is the correct option for this question number 23. Now question number 24. This Legendre's polynomial are said to have dash dash parity if n is even and odd parity if n is dash dash. So this is again, you can draw from the diagram or you can go from the diagram, as well as there is one property of this Legendre's polynomial. That property is already we have seen this property. This Pn of x minus of x is equal to minus 1 raised to n and multiplied by Pn of plus x. That means if I replace x by minus x, so what happens to these different values? For n is equal to 0, we will get P0 of minus x is equal to minus 1 raised to 0 into P0 of x, and here minus 1 raised to 0 is plus 1. So P0 of minus x is equal to P0 of plus x. So parity here of this function is the positive parity or even parity. When we go for n is equal to 1, then according to this property, P1 of minus x is equal to minus 1 raised to 1 multiplied by P1 of x, then minus 1 raised to 1 is minus 1, and therefore P1 of x, and here P1 of minus x is equal to minus 1 times P1 of x. So there is a change of the sign, and therefore it is a negative or there is a odd parity. Then if I go for n is equal to 2, in this case I'll get P2 of minus x is equal to minus 1 raised to 2 into P2 of plus x. Here again this is found to be minus 1 raised to 2 is plus 1, and therefore P2 of x and P2 of minus x and P2 of plus x, they have same sign, and therefore this particular polynomial is said to have even parity. So on the basis of that, Legendre polynomial, as that means it shows that P0, P2, P4 etc., all these polynomials P0, P2, P4, P6 etc., all these polynomials have even parity, and remaining, that is P1, P3, P5, P7 etc., these polynomials do have odd parity, because every time minus 1 raised to odd number gives you minus 1. Therefore there is a change in the sign, and as there is a change in sign, there is change in the parity. Therefore Legendre's polynomial are said to have even parity if this n is even, and odd parity if n is odd, and therefore correct option of this question number 24 is C, even and odd. So read once again the statement. Legendre's polynomial are said to have even parity if n is even and odd parity if n is odd, and therefore as we have seen in this example, P1, P3, P5, P7 etc. all odd Legendre polynomials, they have their parity to be odd parity or negative parity, and for even Legendre polynomials n is even, then all such polynomials they are supposed to have positive parity, and the condition we are going to use here is this: Pn of minus x is equal to minus 1 raised to n into Pn of plus x. You can go for solving this problem by taking the help of the diagrams or the plots what we draw in case of P0x, P1x, P2x etc. That diagram also tells you when x is replaced by minus x, whether the sign of that particular wave, that polynomial changes. If it changes, then it is said to have odd parity. If it doesn't changes, it remains same, sign of the polynomial remains same after x is replaced by minus x, then all such polynomials are said to have even parity. So this particular question can be solved from two aspects. Either you can use this property, or you can go for the diagram which we have drawn earlier. Now question number 25. Following is the Lagrange differential equation. Now this is again a standard form of differential equation. You might be knowing out of these four equations given, first one is x into d square y upon dx square plus 1 minus x into dy by dx plus lambda times y. That is called as the Lagrange differential equation. Then second is x into d square y upon dx square into 1 plus x into dy by dx plus lambda y is equal to 0. That is second equation. Third is C, x into d square y upon dx square plus x minus y in 1 into dy by dx plus lambda y is equal to 0. And final equation is x into d square y upon dx square minus 1 minus x into dy by dx plus lambda y. So this is again a memory question, and therefore you have to go for the correct answer of this question number 25. This is the Lagrange differential equation: x into d square y upon dx square plus 1 minus x into dy by dx plus lambda y is equal to 0. Now you have to go for this particular equation making in the standard form of equation, that is p of x x y double dash plus p of x into y dash plus q of x into y is equal to 0, and then using this, discussing this p of x and q of x, whether at x equal to x0 whether they diverge or whether they converge. Based upon that we can go for a series solution for this. So using the method of series solution, Frobenius series solution method, to solve this differential equation, we come across an infinite series as a solution of this differential equation, and that particular series, if it is in that particular series, if certain boundary conditions are used, what we get is called as Lagrange polynomials. So what we did in case of Legendre polynomials, same thing we can apply here in case of Lagrange polynomial too. So solve this Lagrange differential equation given by option A using the method of separation of the Frobenius series solution method, and get the solution which is an infinite series. Now get the polynomials using certain boundary conditions, and based upon that we get a Lagrange polynomial as follows. So this question number 26, as what we have discussed here, solving this Lagrange polynomial by the method of the Frobenius series solution, we come across a series, and the form of the series given here is this option A, ln of x is equal to summation over r equal to 0 to n factorial upon n minus r factorial into r factorial square multiplied by x raised to r. Now minute changes I have made here. Instead of this making n minus r, I have made here to be n plus r. Otherwise everything is just same. In the third option we have made n factorial upon n minus r factorial into r factorial, not square is not written there, and the last one n factorial upon n minus r factorial and r factorial square into x raised to r. So here this sign or this value of r from r equal to 0 to n, this has been taken infinity, and this is how this particular is not applicable. So therefore this is wrong, this is also wrong, and this is wrong, and therefore correct option of this expression for Lagrange polynomial in the series form is given by ln of x is equal to summation over r equal to 0 to n. It is n factorial divided by n minus r factorial into r factorial square multiplied by x raised to r. So this is again a memory based question. So you have to go for solution of this question number 26 depending upon your memory. Then question number 27 for Lagrange polynomial. Again we have seen this. This is what called as the generating function. Out of these four options given, you have to identify the correct generating function. When the generating function is expanded around t is equal to t0 or t equal to 0, that particular expansion gives you a series in power series in t raised to n with some coefficient, and these coefficients are called as ln of x, and the correct generating function for Lagrange polynomial is this. Option A given by option A. It is 1 upon 1 minus t into e raised to minus xt upon 1 minus t. Expanding this exponential, we get this type of series, and therefore it is 1 upon 1 minus t into e raised to minus xt upon 1 minus t. So this is called as the generating function for the Lagrange polynomial. So using this particular generating function, we can get the Legendre Lagrange polynomials, what we have seen by this equation number 26. So question number 26 and question number 27, we can obtain this expression for Lagrange polynomial using this generating function by expanding it around t equal to 0 as shown by this particular method. Now again there is another method with which one can calculate this Lagrange polynomial, and this method is called as the Rodrigues formula. So Rodrigues formula for Lagrange polynomial, as it has been given, it is given by ln of x is equal to e raised to x upon n factorial into d raised to n upon dx raised to n multiplied by x raised to n into e raised to minus x square. Then this is option A. Option B is ln of x equal to e raised to x upon n factorial d raised to n upon dx raised to n multiplied by x of x raised to n and e raised to plus x. So it is e raised to minus x, here it is e raised to plus x. That change has been made here. In the third option, this x raised to minus n has been changed, then e raised to minus x is as there, and out of this fourth option is also here e raised to x upon n factorial into d raised to n upon dx raised to n in the bracket x raised to minus n into e raised to plus x. So here this as n has been changed here, and e raised to x has been made positive. This x has been made positive. So out of this is again a memory based question. You have to remember the Rodrigues formula for Lagrange polynomial is given by this option A, that is ln of x equal to e raised to x upon n factorial into d raised to n upon dx raised to n multiplied by x raised to n into e raised to minus x, and therefore as we have seen earlier, we can find out different Lagrange polynomials. L0x, putting n is equal to 0, I'll get e raised to x upon 0 factorial multiplied by d raised to 0 upon dx raised to 0 multiplied by x raised to 0 into e raised to minus x. So except this, that means 0 factorial is 1, d raised to 0 upon dx raised to 0 is also 1, x raised to 0 is 1. So I'll get e raised to plus x into e raised to minus x, and that's why it is simply 1, and therefore L0 of x is simply a polynomial for all values of x, positive and negative. This Lagrange polynomial of order 0 is simply equal to 1. We can go for another calculation, L1 of x. So here it is e raised to x upon 1 factorial multiplied by d by dx into x raised to 1 multiplied by e raised to minus x. This time it is a product, so you can use a product rule there, and you can find out the value of L1x, and if it is obtained, this L1x is calculated to be, is found to be so there are different Lagrange polynomials. these Lagrange polynomials can be obtained by this method what we have seen here, and this method gives you 1 minus x. So L1x is simply 1 minus x. We can calculate here. Similarly, if we go for another calculation, L2x, using the same method, Rodrigues formula, if it is calculated, it comes to be 2 minus 4x plus x square. So you can go for this small exercise. Given this Rodrigues formula, put different values of n and get L0x, L1x, L2x, L3x, etc. All Lagrange polynomials can be calculated and can be plotted for different values of x as given in our textbooks. Then next example, question number 29, is again exactly same what we have done earlier. Using this Rodrigues formula, you can find out the L0x, L1x, L2x, etc. Just now we have seen this L0x is simply equal to 1, L1x is simply equal to 1 minus x, and L2x, as we have just now discussed, it is given by 2 minus 4x plus x square. So out of these four options, option B is correct, where L0x is 1, L1x is 1 minus x, and L2 of x is equal to 2 minus 4x square minus x square. And in other options, I have made something here, it is plus sign, then a change of the sign here is plus 4x, and there also it is this minus change of the sign of this L0x is made to be minus 1. So all these options, option A, option C and option D, are not correct. The correct option is this B, which is what we have obtained. L0 of x is equal to 1, L1 of x is equal to 1 minus x, and L2 of x is equal to 2 minus 4x minus x square. So using Rodrigues formula or any other method, generating functions also, we can find out first three members of the Lagrange polynomial are given by L0x is equal to 1, L1x is equal to 1 minus x, and L2 of x is equal to 2 minus 4x minus x square. And also try to plot all these things. You'll find there are other properties too. Now here also question number 30, which is related to this orthogonality property of Lagrange polynomial. Like Hermite polynomials also, this Lagrange polynomial orthogonality condition requires this factor e raised to minus x there. Otherwise this right hand side will not appear to be a Kronecker delta function. So here the orthogonality property of Lagrange polynomial is integral. Now see this integral, this time it is not from minus 1 to plus 1, which is there in Legendre polynomial. In case of Hermite polynomial, it is minus infinity to plus infinity. In case of Lagrange polynomial, this orthogonality condition is from, in the integral, it is from 0 to infinity, e raised to minus x ln of x into lm of x into dx is equal to delta mn. Now here also the orthogonality condition is exactly as what we have done earlier case. In this case, this is equal to 0, and if this delta mn is equal to 0, there are four options given. If m is equal to n, this is not true, then there is certain value for this delta mn. This value is found to be there. If if m is not equal to n, this delta mn is equal to 1, that is also not correct. Delta mn is equal to 0 if m is greater than or equal to n, that is also not correct. And delta mn, or this Kronecker delta function, right hand side takes value to be 0 if m is not equal to n. Therefore, for different degree Lagrange polynomials, this integral along with this e raised to minus x, if it is calculated, this gives me the value of the right hand side to be equal to 0. Therefore option D is the correct option. Delta mn is equal to 0 if m is equal if m is not equal to n. So that is again a question that is memory based. So you have to go for writing this particular orthogonality conditions for Legendre, for Hermite, as well as for Lagrange. Then we can find out this type of things which we have discussed just now. Then this is a three terms recurrence relation. The three terms recurrence relation here for the Lagrange polynomial is, out of this given four equations A, B, C and D, equation C or option C is correct one, that is n plus 1 into ln plus 1 of x is equal to twice n plus 1 minus x into n times ln of x minus ln minus 1 of x that is called as the three terms recurrence relation. As already we have seen, we have to differentiate this Ln of x. So the generating function, whatever we are writing, we have to differentiate first this with respect to t, differentiating with respect to t once, and then rearranging the terms there for t raised to n. We get the equation which is given in the form n plus 1 into L into n plus 1 of x. So this is the Ln plus 1, this is Ln and Ln minus 1. So knowing that L0 and L1, one can find out L2. Knowing L1 and L2, one can find out L3, and likewise higher order or higher ordered Lagrange polynomials, they can be obtained by using these three terms recurrence relation, and the correct recurrence relation for this Lagrange polynomial is given by option C, which is n plus 1 Ln plus 1 of x is equal to twice n plus 1 minus x into n multiplied by Ln of x minus Ln minus 1 of x. So knowing previous two members of the Lagrange polynomials, next member or the new member of the Lagrange polynomial can be obtained by this particular recurrence relation, or which is called as three terms recurrence relation for Lagrange polynomial. Now question number 32, the differential equation 1 minus x square into y double dash minus twice xy dash plus n into n plus 1 minus m square upon 1 minus x square bracket complete into y is equal to 0. Note that this equation contains this additional part as what we have seen here. In the simple or normal Legendre differential equation, this m square upon 1 minus x square is not there, but when this particular Helmholtz equation is when we go for the method of separation of variable of this Helmholtz equation in the spherical polar coordinate system, we come across this equation which is called as the associated Legendre differential equation. So try to understand, this is not a Legendre differential equation. Legendre differential equation doesn't contain this part, whereas it is not a Lagrange differential equation which we have already seen. Also this is not a Bessel differential equation. So this is the associated Legendre differential equation. Now from where this comes is that, as already we have seen, solve this Helmholtz equation. Helmholtz equation, when we separate this separation of variables, if this particular separation of variables is carried out in the spherical polar coordinate, then we come across this equation which is called as the Legendre or the associated Legendre differential equation. Try to understand, this differential equation requires another method to solve that, and getting the solution of this associated Legendre differential equation is called as associated Legendre polynomials. So Legendre polynomials and associated Legendre polynomials, they have a clear-cut relation which we are going to see in further few questions. So here, this is the question number 33. The associated Legendre function is defined as, this is simple definition. Now remember, our Legendre polynomial, we define this is Pn of x. So n is called as order, x is the variable, and this is the polynomial. Whereas this associated Legendre polynomial, which is given in the same form, except this m appears there and x. So now there are two symbols. N is used for one of the order, m is also used for another order, and written this way. So Pnm of x is called as associated Legendre polynomial, and Pn of x is called as normal Legendre polynomial. Now getting this associated Legendre polynomial from normal polynomial, we have to use this expression given here. Out of this a, b, c and d, correct option is this c, which is given by Pnm of x is equal to 1 minus x square raised to m by 2 into d raised to m upon dx raised to m into Pn of x. So this is your normal Legendre polynomial or ordinary Legendre polynomial. It is differentiated, mth differentiation is to be taken along with this factor 1 minus x square raised to m by 2. Whenever this type of calculation is done, what we get is called as associated Legendre polynomial. So getting associated Legendre polynomial from Legendre polynomial, we have to use this mathematical expression which is given by option C. Pn of x is equal to 1 minus x square that raised to m by 2 into d raised to m upon dx raised to m into Pn of x, and based upon that, let's see one more equation here. Question number 35. For associated Legendre polynomials, now I am writing Pn0 of x is equal to Pn of minus x, Pn0 of x is equal to minus Pn of x, Pn0 of x is equal to Pn of x, and option D is Pn of 0 of x is equal to P minus n of x. So out of this, as we have just now seen, so here when we go for this particular, again you can take the help of this particular example here. This is according to our definition, Pnm of x is defined as 1 minus x square raised to m by 2 and multiplied by d raised to m upon dx raised to m into of Pn of x. So here we have to put m is equal to 0. Therefore, I'll write here Pn0 of x. So this is associated Legendre polynomial of order n, and this another coefficient is 0 here. So that will be given by 1 minus x square, and this is 0 upon 2 into d raised to 0 upon dx raised to 0 into Pn of x, and therefore 1 minus x square raised to 0, this is 1, d raised to 0 upon dx raised to 0, that is also 1, so into Pn of x. That means this associated Legendre polynomial Pn of x, Pn0 of x is equal to simply Pn of x, and therefore the correct option of this question number 34 is C, Pn0 of x is equal to Pn of x. That's why the correct option is given according to this. Now, as from this example we have seen, for associated Legendre polynomial Pnm of x is equal to 0, provided, now there are two coefficients we are using, either n and m. If m is greater than n, so see in this formula where we have seen this expression, so we have to get this mth differentiation. Now if I am getting this mth differentiation of Pn of x, provided this m is more than n, so then this particular side or here this particular equation becomes simply 0, and therefore Pn of x, Pnm of x is simply equal to 0 provided this m is greater than n, and therefore this correct option of this particular question is this option B. So for associated Legendre polynomial, if m is greater than or equal to, if m is greater than n of x, actually there should be not this symbol, there should be m is greater than n. So if m is found to be greater than n, then such type of associated Legendre polynomial is simply found to be 0, because we have to get mth differentiation of the term which is containing x power raised to n, and whenever m is greater than n, this differential is found to be 0. Therefore question number 35, correct option is m greater than n. This is called as associated Legendre polynomial. Then question number 36, angular part of wave function of hydrogen atom is written by using associated Legendre function, then Bessel function, and the Henkel function. Option D is the spherical harmonics. Now that is what already we have discussed in the class 2, that solve this Helmholtz equation by method of separation of variables. In that case we come across this theta and phi part equation. So here our solution psi of r theta phi is taken to be a solution of this r of small r, and another, this is called as the y, that is Lm, and this is a function of this theta and phi. So this particular function which is obtained as the angular part, so this radial part is there, this is the angular part, and here this particular part is called as the angular part which depends upon theta and phi, and therefore angular part of wave function of hydrogen atom is this part which is called as spherical harmonics, and therefore this question number 36 option is correct option is D. Now in this spherical harmonics we have theta part equation and phi part equation. That theta part equation has a solution which is associated Legendre function, and the phi part solution is this is going to be, that is going to be the e raised to I m phi. that is exponential solution. So this particular wave function, angular part of wave function, which is function of two independent variables theta and phi, and therefore this YLM theta phi, that is called as spherical harmonics, and which can be obtained in the following way. We are going to discuss in the following problems. Question number 37. Associated Legendre polynomial P11 of x if Legendre polynomial P1x is equal to simply x. So again, try to find out this by the same formula what we have seen here earlier. This Pnm of x is given by 1 minus x square raised to m by 2, and it is d raised to m upon dx raised to m into Pn of x. Now here in this case we have been given n is equal to 1, m is also given to be m1, and therefore P11 of x is equal to 1 minus x square raised to 1 half, that is square root of this 1 minus x square, and this is d raised to 1 upon dx raised to 1, that is d by dx of Pn of x is given to be simply x, and this differential of x with respect to x simply is equal to 1, and therefore it is 1 minus x square that raised to plus half, and therefore C is the correct option. P11 of x, associated Legendre polynomial, which can be obtained from this normal Legendre polynomial Pn of x, is found to be 1 minus x square raised to plus half, and that's what question number 37. Correct option is this C, that is P11 of x is equal to 1 minus x square raised to plus half, and that is can be calculated as we have seen by this example. Now question number 38. The associated Legendre polynomial Pnm of x are obtained from normal Legendre polynomial Pn of x by differentiating m times with respect to x. Following is the correct expression. This is again a repeated question, so option B is the correct option. Pnm of x is equal to 1 minus x square that raised to m by 2, and mth differentiation of Pn of x, that is d raised to m upon dx raised to m of Pn of x, if it is calculated, this is found to be right hand side of this expression is found to be the associated Legendre polynomial, and this is our normal Legendre polynomial. So getting this differentiation and calculating this way, we get associated Legendre polynomial from normal Legendre polynomial given by option B. Now, as we have discussed earlier, question number 39, the correct expression for spherical harmonics. Now there are four options given. As we have already discussed, this option A is YLM. Y is the symbol used for the spherical harmonics, which is function of two independent variables theta and phi, given by capital N into e raised to im pi, multiplied by this PLM of cos theta. Now replacing this x by cos theta, we obtain, that is called as this associated Legendre polynomial, and that is the part of the spherical harmonics. So here this is the solution of this phi part equation, this is the solution of the theta part equation, that means the differential equation in theta, that is solution of that is going to be the associated Legendre polynomial PLM of cos theta. This is the solution of this phi part equation, and n is the called as normalization constant. So in general, YLM theta phi is given by this n into e raised to im pi PLM of cos theta. So this is normalization constant, and that's what this is the correct expression for the spherical harmonics. Remember what changes we have made here. This is written to be root n, so e raised to im pi into PLM into cos of theta. Actually this and this is not different, that means I have root n here written, otherwise there is no change here. Still this is more appropriate answer is this option E. Here it is written to be n times e raised to minus im pi. This is not going to be a correct form because of this negative sign there. Then fourth is n by 2 into e raised to im pi PLM of cos theta. Here also, as I said here, n, root n, n by 2, etc. These are normalization constant. As they are constant, they can be written either this form, or this form. But in general, in quantum mechanics and mathematics of physics, we use, this is the form of this correct expression for this spherical harmonics, which are going to be this solution of the angular part of Schrodinger equation when it is solved in case of the spherical polar coordinate system. So in quantum mechanics, you are going to learn this particular expression. You have to solve a Schrodinger equation in the spherical polar coordinate system, separate r part equation and separate theta and phi part equation, which is called as angular part equation. Solution of that angular part equation is given by the spherical harmonics, and the exact form or standard form for that is ylm of theta phi is equal to n times e raised to I m pi into plm of cos theta. So out of that, just try to understand, this is our spherical harmonics, then this is the phi part equation, and this is what your associated Legendre polynomial. So how associated Legendre polynomial and the solution of phi part equation collectively gives rise to the spherical harmonics, which are the expressions of the wave functions. So the different wave functions where what we obtain in case of the hydrogen atom. So these wave functions where sometimes it is circular, sometimes it is elliptical, sometimes it is this dumbbell shape. All these are the spherical harmonics which is given by y00 or y10 of this theta and phi, that is spherical orbits. Then other orbits are given by this y11 theta phi and y21 theta phi and etc. So all these are the wave functions or the actual wave functions where this electron goes in the higher orbits. These wave functions take different shapes and sizes. So all this can be drawn, and they have their equations can be given by this all the spherical harmonics. So more about this you learn in quantum mechanics when we go for the solution of hydrogen, the discussion of the hydrogen atom using this Schrodinger equation for hydrogen atom. You will come across all these spherical harmonics and the corresponding equations for that, which is associated with this associated Legendre differential equation and associated Legendre polynomials and so on. So expression for the spherical harmonics is given by option A, which is given to be the correct one. Now this is again a repetition question what we have seen here. This is the generating function g of xt is equal to e raised to x into t minus 1 upon t upon t2 is of, this is Legendre polynomial, Lagrange polynomial, then Hermite polynomial and Bessel polynomial. So this generating function, this is the generating function given for this is what given for this the Hermite polynomial. Okay, so you have to remember this is the expression for this Hermite polynomial, and we can remember this is again a memory equation as we have seen there. So these are the in all 40 questions we have seen in the video 1 and video 2, wherein we have seen different properties of 4 different types of special function, that is Legendre differential function, Legendre polynomial, Bessel polynomial, Hermite polynomial and Lagrange polynomials. So what we have to go for when we go for actual study of this particular module or this chapter, when we go for actual examination, so go for all special functions. So first see what are there the expressions or the first differential equations for all such of this. Then once we go for that, then go for actual polynomials, so series solutions. So we have to go for this series solutions. Then we have to go for the generating function for each, as well as we have to go for a Rodrigues formula. So generating function, Rodrigues formula, series method and this differential equation. From that we can obtain all such 4 special functions. Then we have to go for properties. So all the properties, out of this the 3 terms recurrence relation. So this 3 terms recurrence relation and the another property, that is the parity of that particular type of polynomial. That is important properties. Based upon that there can be several equations. And another important aspect what we have seen, go for this orthogonality condition for all these polynomials. So all orthogonality conditions for Hermite polynomial, for Legendre polynomial, for Lagrange polynomial, we have to remember whether what is the right hand side, how it is canonical delta function, what are the different conditions on this m and n. All these things are to be remembered. Along with we have to go for this associated Legendre differential equation. So what is the difference between normal differential equation and associated Legendre differential equation. What is the solution of normal Legendre differential equation and associated Legendre differential equation? What is the connection between these two, which we have seen earlier several examples. PLM of x is equal to 1 minus x square raised to m by 2 into d raised to m upon dx raised to m of that particular thing. So this type of things what we have seen here. So such type of relations we have to go for. Along with that, also there are certain properties of this associated Legendre polynomial. Its orthogonality condition is also there. So write all these orthogonality conditions one by one. Write generating function of each special function. Write Rodrigues formula of each generating function. Try to get first few polynomials, like means Legendre polynomial, Harmite polynomial, as well as Lagrange polynomial using this generating function. Sometimes try to plot all these polynomials. Now plotting these polynomials again gives a lot of information about these polynomials, their properties, their parity, etc. Even orthogonality of these polynomials also can be studied from the graphs which we draw when we go for study of all these things. So this is what in general the important questions from this module 3, which is for this mathematical methods of physics for this coming examination of Savitribai Phule Pune University. I hope you'll find all these questions interesting, simple, easy to understand and conceptual based. That will help you in this particular example. Now apart from this, I'll give you one more website. There is one very nice website. If you want, you can go for this website. This is www.sanfoundry. Sanfoundry, okay? SANFOUNDRY, sanfoundry.com. This website gives many questions on this type of special functions. Some of the questions I have taken here from that website. You can go for its explanation, you can go for its answer, you can go for some other difficult questions or MCQ questions from this particular website. Along with that, there are several other options, several other sources are there from which one can go for all these type of the MCQs on this particular module, that is number 3, that is special function. Thank you all.